Okay. All right. So usually I record every lecture to the cloud. So each one of us, each professor has a Zoom account with limited space. So I only keep this recorded lecture for a week. Is that okay? Yeah. So yeah, try to if you want to review it, so try to do that within a week. So this week I'm gonna remove the recording from last week and keep the link for this week, and you have another week to review. So this is the plan. All right, let's get started. Okay. All right, so can you see my screen? Okay. Okay, so before we continue, so let me very briefly summarize what we have covered last week. So we have talked about the genetic maps. So there are two measures for measuring the genetic map distance between loci A and B, right? One is additive, so we use X to represent the number of crossing over occurring between these two loci in average per meiosis. So this is one way we can use to measure the distance, genetic distance between A and B. There's another way, there's another measure we can use to do the same thing. So, but that one is non-additive. We use the R recombination frequency to represent how frequently we can get a crossover in between these two loci. So this is another measure for the genetic distance. And because they are doing, they are measuring the same thing, but in a different way. So we so next we introduced the map function. So the map function is a function that can describe the relationship between these two measures. So we try to relate the additive X with the non-additive R. So there are two commonly used map functions. One is the Haldane function. So we have covered this this function last time. So this was where we left, right? So we're going to continue from here. So so since you do not have any questions about this, which is good, so it means okay. So we are okay with this one. So the Haldane function in this map function, in Haldane function, so we assume C equals to 1. C is the coincidence coefficient. Equals 1 means there's a completely interference between these two regions, right? So completely independent. I'm sorry, so these two regions are completely independent, means there's no interference between these two regions at all. So if this is the case, so the map function will become this in this form, and this is the famous Haldane map function. All right. Okay, now Kosambi function. So remember this part. Let me use this. So please remember this part. So this is the common part, right? Common part. Now from here, if we rearrange this equation a little bit, so we're gonna have this. So this is the same from the previous page. So if we rearrange this equation a little bit, so look at here. So we have a C here, right? The C is the coefficient, the coincidence coefficient, and 1 minus 1 minus C equals to I. So I is the interference coefficient representing the strength of interference between these two regions, region 1 and region 2. Okay, now what is different from the Haldane map function from here is in the Kosambi map function, the C is not equal to C is not equal to 1 anymore. So we let C equals to this, the 2 times the R of X. So what is this? This means like we do not assume the independence at all. Here we use a we use a coefficient for a number for C, which is more which is closer to the reality. So so remember, 1 minus C equals to the interference coefficient, right? So here we allow the interference between region 1 and region 2 decrease with the distance. Yeah, that's intuitively this makes sense, right? Because so if the two regions are close to each other, so we think if we will assume if there's a crossing over occurring in region 1, so this crossing over will completely prevent another crossing over occurring in the region 2, which is close by. So this is completely interference. But as long as these two regions are getting removing apart further, so this interference will become less. So yeah, this makes sense. So the interference decreases with the distance. All right. Now, if we let C equals to the function of this, 2 times of the Rx, if we replace this, so we plug this into here, C, then the function will become this. And then, so if you follow this flow to do a little bit algebra, so you can end up with this. And because we want to describe the function of Rx, right? So if you rearrange this formula, so you're gonna end up with this. So this is another famous map function, Kosambi function. Any questions? All right, so the two difference here. So in the previous one, previous page, when we talk about the Haldane map function, so where C was equal to 1, right? But here we allow C to vary, because this C, which represent the interference strength between these two regions, and the interference will decrease with the distance between A and B. All right, so if you do not have questions, we're gonna move forward.
I have a question.
Yes, go ahead. Right.
How did you transition from the series of derivatives and then to an integrals to the to the natural logs? That was the biggest jump.
Here, right? Oh, that's very complicated, but yeah, it's not required for you, but yeah,
I'll ask you later.
Yeah, sure. So I just put down the very so this is a simple version, but if you want to do this, so I think there's a little bit more derivation steps here, but once you finish this, you will come from here. You will come from here to here, and then if you rearrange this a little bit, so you can. So you just rearrange this to solve this part, right? So you're gonna end up with this. Okay, so yeah, so this is not required for the final exam. So for the final exam, so for example, I could give you a question like this. So what's the difference between these two map functions, the Haldane and the Kosambi? So so I think the simple answer to that question is like, okay, the difference, the major difference is between these two is the C. All right, so in the Haldane, so we don't, we just give C a constant equals 1, right? C equals to 1 by assuming these two regions, region 1 and region 2. Region 1 represented the distance between A and B, right? Region 2 represented the distance between B and C. So in Haldane map function, we assume these two regions are completely independent. That's why C equals to 1. So I'm going to talk about this a little bit later, soon. Yeah. Okay. But in the Kosambi map function, so this is not the case. We allow C to vary. All right. Okay. Now this slide shows the difference. So okay. In the Haldane, you're gonna see here, right? There's no C here. So because C equals to 1, that's why you see this. This is the map function between the map distance between A and C equals to the map distance between A and B plus map distance between B and C minus something, but there's no C because C equals to 1. However, if you use the Kosambi, so here we allows the interference to occur. So then you're going to see this map function. So on the left-hand side is the distance between A and C. On the right-hand side, you just use the distance between A and B or B and C to form a formula to express the distance between A and C, right? All right, so now look at here. So I showed this diagram before. So this shows the relationship and distance between these two map functions. So the dashed line is the Haldane, and the solid line is the Kosambi. Okay, so if you look at the very beginning or at the very end of these two curves, they are very close to each other, right? Which means, so if the distance is very short, which means like there's a very strong interference between these two regions. And so in this case, so there's a completely interference. So these two functions are close to each other. They're doing the same thing. If the distance is too large, which means like these two regions, 1 and 2, are completely independent. So these two functions are still performing at the same level. The only difference is in between, in the middle. So if as the distance between the region 1 and the region 2 are increasing, then the interference is decreasing. So these two functions are different in the middle region. Does that make sense? If the region is very small, or if the region is very, very large, like 2 ends here, so these two functions are the same, identical, because yeah, they're doing the same thing, right? Because when the region of interest is very small, so there's a completely interference. Do you agree? If think about a very small genomic region. So if you already have a crossing over in this region, so this crossover will completely prevent another crossing over occurring. Do you agree?
So yeah. The x-axis stands for what? Are they the centimorgan distance or what?
Yeah, the x is the additive measure of the genetic map. Yeah, you can also use the centimorgan to represent that, but x is an additive measure which is measuring the average crossing over, number of crossing over per meiosis. But R is the same thing. Yeah, R can measure the centimorgan as well, but R represents the frequency of the recombination. So the map function actually here is a function that try to find the relationship between the X and the R. X and R are two measures for the genetic mapping distance. However, X is an additive one and R is a non-additive one. So we use the map function to describe the relationship between these two, right? Now we have two versions of the map function. They are almost identical when we are dealing with the genetic distance, which are very small or very large, because these are two extreme situations. So when we are talking about a very small region, so there's a completely interference. So when you have the first crossing over, so this crossover will prevent another crossover occurring. However, if this region is extremely large, we can think about like any region within this big region are independent. So even you have the first crossing over in some place, it will not affect having another crossing over in another region. So this is why these two map functions are doing the same thing, identical at these two regions. They are close to each other, right? However, the only difference between these two map functions is in the region, in the area in between. Because in this middle region, if the genomic distance of interest is neither small nor large, so there's some certain level of the interference between the two crossing overs, if this is the case. So that's why we see the difference between these two map functions, right? Because the major difference, so this could be a question showing up in your final exam. So let me know what's the difference between these two versions of the map function. So the right answer is, okay, so in the Haldane function, so we do not assume the interference. So the regions are totally independent, so C equals to 1. However, Kosambi, we allows the interference to occur, and the interference level will decrease as the distance increase, right? Any questions?
So is it better to always go for Kosambi?
I'm sorry, say that again?
Is it better to always try Kosambi instead of Haldane because we don't know if they have interference or dependence?
Yes, I would do that because the basic model, the fundamental model. So the Haldane is the first one. Was the first one. So because usually like when we develop a series of theorems, so we start from the very basic, easy one, right? And the later on models were built upon that. So they make model better and better. And the Kosambi is a later version. So I think it's more, it's closer to the reality. So yeah, it's better to use Kosambi. And there are some other versions to deal with some, because for either of this, we assume the crossing over is evenly distributed on the chromosome, right? But we know this is not true. So there are some other versions, so very complicated. But this class only gives you some idea about the basic, very fundamental theorem. But in the future, if you do research and if you need to use this kind of map function, so based on what your research situation would be, so you can choose some other version as well. For example, you can consider the hotspot, or so yeah. So did I answer your question? Okay. Yes. Any other questions? Okay, let's move on. All right. So okay. By the way, so so for the first few chapters, so I try to slow down because in this chapters, in this first chapters, so it's quite solid theorem. So I try to slow down to make sure everybody understand the fundamental things. And later on, when we talk about the application of this theorem, so we can go very super fast. Yeah, so this is the plan, the planned pace. All right. Okay, so I think this is the last slides for the first lecture. Okay, so this slides just give you another way to derive the very basic Haldane map function. So using another way to derive this. So to understand this, so we need to know the theorem about the Poisson mass function, that Poisson distribution. So here if we think about that the crossing over is a rare situation, yeah, which is true, because crossing over occurs in the meiosis, but it is not that often. So we can treat recombination as a rare situation. So in statistics, so we have a perfect model, Poisson distribution, to model the probability of having number of events which are rare. So if we define the T as the number of the crossing overs in a region X, so here the X is a region. So we want to calculate the recombination frequency in this region. So X is the additive, right? The map distance. And if we want to calculate the non-additive recombination frequency, so how can we use the Poisson distribution to help us to do the calculation? So this slide shows this. All right. So if we want to calculate within this X region, so what's the chance for us to see T numbers of the crossing over? So we use this mass function. And okay, now if we want to calculate the recombination frequency for X, right? So as we discussed it before, so owning the odd number of the crossing over will contribute to this recombination in this region. Is that correct? Right. So that means like if we want to calculate the recombination frequency within X, so we need to add up all the possible probabilities. So what's the chance? What's the probability that you observe a single crossing over in this region? So if there's a single crossing over, you're going to see the recombination, right? So there's another way. So if there are 3 crossing overs occurring in this region, you will also see the recombination, right? So you will be able to see the recombination. So we have to add up these 2 probabilities and so on. So if there are 5, which is very rare, but it's possible. So if we have like 5 crossing over, you also can see the recombination in this region. So we add up all these probabilities together, and which is equal to this. And if you do some algebra, so you can end up with this. So this is the same with the very basic Haldane map function. So this is the way to derive this. It's not required for you to memorize this or to, so you just understand this. So there's another way we can derive this Haldane map function. Sorry, I always have trouble to pronounce these names. Haldane. Okay. All right, so congratulations, we are done with the first lecture. So far, any questions?
Any question, Professor.
Sure.
So in general, how do we know that 3 crossovers happened? Because it would still produce the same result as 1 crossover, right?
Yes, because we're talking about the region between A and C, right?
Mm-hmm.
A and C.
Yeah.
So if we do the test cross, we only identify the progeny carrying the recombination, recombinance between A and C, right? So if there's only one crossing over, yeah, we're going to see the recombinance in terms of A and C. If there are 3, the same. If there are 5, the same. But if there are 2, so you're going to see the parental type, so there's no recombination. So that's why we only add up the probability of having odd numbers of the crossing overs. All right. Okay, so the second chapter so the first chapter we can understand. So the recombination frequency R is an important thing, right? So that's the thing we are very interested in. So in the second chapter, we're gonna see how in different test cross, in different experimental design, how we can use the data, use the design to help us to calculate the recombination frequency, which is R between 2 loci, A and B. So here we want to calculate the recombination frequency R between A and B for what? For what? Have you had chance to read the textbook? Yeah, good. So okay, now the first chapter we talk about the recombination frequency. We want to see how we can how we can use benefit from the map function to do the calculation, right? So now in chapter 2, we're gonna use different designs, different experimental designs for the test cross to measure this thing, R, recombination frequency between loci A and B for two things. It's important. I may give you some questions in the final to ask what's the purpose for to calculate the R, right? So one is to measure the distance between A and B. Oh, no, sorry. The first actually is to test if A and B are linked or not, right? So we want to test the linkage between A and B. If they are linked, then we can do the second thing. So what's the distance, genetic distance between A and B, right? So this involves 2 steps. The first step, if we calculate it, if we use the map function to calculate a realized value for this R, so we can test if this R equals to 0.5 or not, because 0.5 represented the non-linkage, right? So first we can test if these 2 loci are linked or not. If we are sure these 2 loci are linked, if they are linked on the same chromosome, and then second thing, we can do the calculation to measure how far they are removed from each other on the same chromosome. So these are the two things we can do based on the recombination frequency R. Okay, so as I mentioned, so in this lecture, in this chapter, we're gonna talk about the 2 primary experimental design here. All right, we can use these two design to do a test cross to produce many hundreds or thousands progeny from the test cross, and we can count the progeny carrying the recombinance between A and B, right? And then do the calculation to calculate R. Once we have R, we can do the test, either linkage test, or we can calculate the distance, the distance between this A and B, right? Okay. And after we, when we talk about each design here, we're gonna introduce different statistical algorithms or method to help us to do the hypothesis testing or the calculation. So this is what we're going to do in chapter 2. All right. Okay, so this is very this is simple, right? So I have shown this slides to you last week. So this is a very classical backcross design. So what is the backcross design? Which means, okay, so this is the F1 parent, and we cross this parent back to the very first parent, the double homozygous tester, right? And we're going to generate these 4 genotypes. And from this 4 genotypes, from all this progeny, we're going to identify the proportion of the progeny carrying the recombinants. So these 2 groups represent the progeny showing the non-parental genotypes, right? All right. And we can do a very easy calculation using this formula to help us calculate the genetic distance between these 2 loci. All right, so this is easy, right? Any questions? Good. All right, so let's look closer to this design. So this is the backcross design. So usually we use the BC to represent this backcross design. And we start from 2 pure parents in terms of these 2 loci. So here we only talk about the 2 loci, A and B, because we want to see if these 2 loci are linked or not. If they are linked, what's the distance between these 2? All right, so now we start from 2 parents, 2 pure lines. The first parents are the double homozygous. So which means like, so the first parent at this 2 loci, the first parent have the homozygous A1 allele, and another locus B1 allele. And for the second parent, we have A2 allele and the B2 allele at this 2 loci. So if we cross this 2 parent, we're going to end up with the F1, which is the dihybrid, so the double heterozygous. And now we use this to go to back cross to 1 parent or the other one. So this is called the back cross, right? So if you use this dihybrid, the double heterozygous, to cross either pure parent, and you're gonna end up with 4 different genotypes here. Is that clear? Okay, so think about think about the situation a long time ago when Mendel did his experiment. So at that time, there's no such thing called the genotyping or the sequencing. So Mendel can only leverage the traits, the dominance or recessive relationship traits to trace back to the genes, right? But now, because we have so many choice of the advanced genotyping technologies, so we can easily sequence and genotype the DNAs to see the alleles, right? Different alleles. So now, so if we use the molecular level genotyping strategy, so nothing can be hidden, right? So nothing can be hidden. Then so there's no such thing like the dominant or recessive. So every allele can be seen by sequencing, right? So in this case, we can say, so all these alleles are the co-dominant. So at a molecular level, so they are phenotypes, molecular level phenotypes that we can observe. So this can help us a lot in the genotyping, right? Okay. All right. So okay, let's see the example back to the Mendel's time. So at that time, so because gene is not observable, so he can only use the phenotypes here. So the phenotypes are linked to the genotype, and it was only possible for him to finish this, to accomplish this study if the genes had the alleles for the genes have the relationship dominance and recessive relationship. So that's the only way that he can observe the phenotypes for the progeny and finish the test. All right. So if these two genes are not linked, one gene is controlling the cis color and the other gene is controlling the cis shape. So, okay, so these two genes are on two different chromosomes. They are not linked. So that's why when Mendel did this test cross, so the results, the experiment end up with four roughly equal group of the progeny. So if you look at the ratio of these two groups, it is 1 to 1 to 1 to 1. So this indicates the low linkage between, there's no linkage between these two genes, right? Two loci. All right. Now, if we can sequencing the DNA, so we don't need to look at the phenotype. We just look at the, we don't need to look at the traditional phenotype. We can just look into the genotype of these two loci, and this we can treat them as the phenotype at the molecular level. All right. Now, suppose we did the same test cross, and we end up with 4 categories. Each category has a unique genotype. Is that clear? So any questions so far? So if we do the test cross, so any questions about this? How did we get this? So this is the back cross, right? So suppose
the same distribution as before, right?
I'm sorry?
That's the same distribution as we had in the previous slide. It's
yes. Okay, no, it's not different. No, I cannot say that is true, because we knew in this situation, these two genes are not linked. That's why you're gonna see this distribution, 1 to 1 to 1 to 1.
I didn't mean distribution. I used the wrong word. I meant just you're using A and B instead of Y and R in this case.
Yes, sure. Yeah, that's right. So so this is the result. Actually, if we cross this individual, F1 dihybrid with this parent, right? If we do this, oops, we're gonna get this result. Is that clear? All right. Now, okay, we can do the same thing as Mendel did, right? We use this cross, the back cross experimental design to generate lots of the progeny. So the progeny, if you look into the genotypes or molecular level phenotypes of these two loci, you're gonna divide all these progenies into 4 categories like this. Am I right? Am I right? Suppose you have two loci, you can divide this big N, 1,000 progeny into one of these 4 categories, right? Right. Oops. So it shows like my internet connection is not stable. So can you still see my slides? Okay. All right. Yeah. Now this is the data. Okay. This is important. So when we do the statistical analysis, we need to get the data, right? So this is what we have from this experiment. So for each category, we will have some numbers here. That's the data. Okay. Any questions? It's not easy to write in this way. All right. Okay. Now, assume these two genes, these two loci are linked. And the distance between them is measured by this number, R, recombination frequency. So what is the recombination frequency here? This R represented the frequency you're going to see the recombinant progeny from the entire group of the progeny. Is that right? Is that right? The fraction or the probability that you're going to see a recombinant progeny from the pool of the progeny. Is that right? All right. So, okay, look at the first genotype. Is this one a parental type or non-parental type?
It's a parental type.
Parental type, right? Parental type means there's no crossing over occurring between these two loci. Is that right? Yes. Okay. So that's 1 minus R. Do you agree? What's the chance for you to get a parental type? 1 minus R. Because R represents the chance that you get a recombinant protein, right? Okay. And this category only represents half of the group that you get the parental type, right? The other half is where? It's here. This is another parental type, is that right? So this takes another half of this 1 minus R. So the total fraction of having the recombinant progeny is 1 minus R. Do you agree? The entire chance is 1, right? So if you look at all the progeny, that's 1. But out of this progeny, what's the fraction of the progeny carrying the parental type? 1 minus R, right? So look at here. So this is the total progeny from this experiment. So you can divide this many progeny into two groups. One group represents the parental type and another group represents the non-parental type. Am I right? Am I right? What's the fraction? R and 1 minus R. So you will have 1 minus R of that many parental type, and you're gonna have R proportion of the non-parental type. Is that clear? Okay. Now within, so if you only look into the parental type, half of them will carry this genotype, and another half will carry this genotype. Am I correct? Am I correct? That's why you're gonna see a 1/2 here, right? 1/2 here. So these two portions add up to 1 minus R, which represent the progeny carrying the parental type. Does that make sense? Okay, now it's clear for this two. I don't have to spend time on that, right? Because totally out of this 1,000 progeny, you're gonna see R this many non-parental type. But if you only look at the progeny carrying the non-parental type, half of them will carry this genotype and another half will carry this genotype. Is that correct? So now it's clear how we understand this table, right? So this is the results from the experiment. We're gonna end up with this data. So this is the real data and this is the expected frequency out of this experiment. Any questions?
So because Mendel didn't know that like genes were linked, he got the proportion of 1 to 1 to 1 to 1?
Yes.
Okay.
So yeah, that's the classical Mendelian experiment. So in that case, okay, so this is a very classical example. I usually give this example in my introductory genetics class. All right, because these two genes are not linked. They are on two different chromosomes. So if you do this kind of test cross, you're gonna see these results. Oops, yes, these results, roughly 1 to 1 to 1 to 1. So this makes sense. Okay, so so in this case, let me ask you a question. In this case, what is the R? What is the value for R?
0.5.
Yes, very good. So in this case, R equals to this, right? Okay, remember this? So if you replace this R equals to 0.5, what is that? Can you do the calculation? What's the first number here?
5%.
Yeah, this is 5%, 50%. So 1 minus 0.5 is 0.5 and divided by 2. This will be 0.25. Is that correct? How about this one?
The same.
The same. So this is a very general formula. So if these two genes A, B are unlinked, so you're going to end up with what? 1 to 1 to 1 to 1. Am I right? Am I right? If R equals to 0.5, which is the previous case, right? So if these two genes are not linked, we can still use this formula. But now R equals to 0.5. If you plug this R equals to 0.5 into this formula, you're going to end up with a ratio of 1 to 1 to 1 to 1. So that's correct, right?
I have one question.
Yeah.
The whole point of finding R was to see whether like genes were linked, and now by finding R, we are like saying that these genes are not linked. Like is that?
Okay. Yes. So yeah, I think you're right. So this is related to the first question I just asked when we start this lecture. So what's the purpose? Major primary purpose for us to calculate this R, right? So the first thing, we can calculate this R from any of this kind of experimental design. For example, the backcross design. Once we get this data, we can calculate this R, right? R estimate. We can use this data to calculate this R. So if you see this R equals to, for example, 0.43, what does that mean? 0.43. Do you believe these two genes are linked? I don't know, because the 0.43 is so close to 0.5. So it could be like these two genes are not linked, but because of some sampling error, you end up with a calculation which shows R equals to 0.43, right? Okay. So we need to test.
So when R is equal to 0.5, they are not linked.
Yes, okay. That's right.
And does this like mean if it falls below half, does it mean like interference, or it's not related?
Right, you are right. So if there's an interference, so even there's an interference, so this R, if we do this kind of design to calculate R, right, you will never see R goes beyond 0.5. So the 0.5 is the upper bound for this.
Yeah, okay. But then 1 minus R would be above 0.5.
That's right. Yeah, that's right. Yes,
so
yes.
Take R
good point. Yeah. So yeah, this is what we can have, the maximum value for R. Oh, so in this case, R equals to 0.05.
Okay.
For the non-linkage. So if these two genes are unlinked, if they are on the on two different chromosomes, you're gonna see this, right? 1 to 1 to 1 to 1 to 1. And if you use the map function to calculate the R, so the maximum number for R, the maximum realized value for R should be 0.5. So all of us should memorize this. So the R cannot go beyond 0.5. Otherwise, go back, check your calculation.
Okay, thank you.
Yes. Any other questions? Good question. Yeah. Okay. All right. So is that clear? So here we try to use backcross experiment to collect some data, and then we're going to use this data to calculate this R. So now next, I'm going to show you how we use this data to calculate the estimation of this R. Okay. So before we go into that step, so I'm going to introduce a very important concept, statistical concept to you, maximum likelihood estimation method. So have you heard this term before?
Yeah.
Okay, good. So if you have taken any statistical classes, so usually in any statistical classes, a professor will cover this term. All right. Okay, so in statistics, the MLE, maximum likelihood estimation, is a method for estimating the parameters. So we have a model, right? We have a probability model. So in statistics, usually the model-based method. So once we use a model-based method, we need to specify a model. And once you have a model, you must have some parameters, right? For example, normal distribution. If you assume a normal distribution, you must have how many parameters in normal distribution? 2, right? You need to have a mean, mu, average, and you need to have another thing called the sigma, the standard error, right? Standard deviation, right? So these are the 2 parameters we need for a normal distribution. Okay, now maximum likelihood is, okay, now if we have a model and if we have parameters, but unknown parameters, so this is the way we can use to analyze your data and to estimate the parameters, right? Okay, so what is the MLE for the parameters of a statistical model given the data? So we use this method to try to find the parameter values, try to find the solutions for these parameters that can maximize the likelihood of making this observation given the parameters. I'm not sure if it is clear. The definition is kind of like, yeah, hard, but yeah, if you read it a couple of times, I think, yeah, you will be able to understand this. All right, so let's talk about this. All right. I think, yeah, usually I would like to give you a simple example to demonstrate the theorem here. Okay, so suppose we have a model. So we want to do this experiment. So here is a guy. So he want to check if the coin he used for gambling is a fair coin or not. All right. So this is the target. So he want to do some experiment to check if this coin is a fair one or not. All right. Okay. So now he did an experiment. He tossed this coin for 100 times and end up with a case like this: 50 times with a head and 50 times with a tail. Okay, so this is the thing. And now, because I want to demonstrate the maximum likelihood method, so we need to have a model. So probability model, here we use a binomial model. So have you learned about the binomial model? All right, good, very good. All right, so this is the binomial model. Okay, now look at here. So if we think each toss, so we have 100 tosses here, right? So if each toss is independent from each other, so when we want to calculate the joint probability, we can treat each event as an independent event, right? And the joint probability will be the multiplication of each probability, right? So this is the model. So we use this function to represent this density function. given this unknown parameter here, theta. So what's the chance you're gonna see the first outcome, the second outcome? So this is the first outcome given this model and the parameter, and this is the probability of the second outcome from the same model, right? So if you multiply these probabilities together, that gives you the joint probability. The joint probability of this 100 tosses is like, so given this parameter, I'm gonna talk about this parameter a little bit later. What's the chance you're gonna see this series of the outcomes, right? And the likelihood is defined as this. So for example here, okay, we use a binomial distribution here, right? So since you all know the binomial distribution, so what is the parameter for binomial distribution? Can anyone let me know? Can anyone tell me what is the parameter, single parameter we use for binomial distribution?
The chance to get the success?
Sorry, say that again.
Like the chance to get success in one trial.
Yes, yes. Okay, very good. So if we believe this experiment is following a binomial distribution, we're going to use this P here, right? The P represented the probability of being successful. Which depends on what's the definition for the success, right? So if we define like a head, landing a head with a head is a success, then this P represented the probability of having a head, right? Okay, now, so this is the likelihood here. So what's the probability that if this guy tossed this coin for 100 times, it end up with 50 successes and 50 failures, right? So that's the probability. Oops, this is too messy. Let me discuss this. I wish I could have a whiteboard for you to write this. So it's so hard to use the PowerPoint to show this. All right. Okay. This join the probability for the experiment, right? Okay, now for this experiment, we have 50 success. Oops. Am I right? And we have 50 failures, right? The joint probability, if we treat each toss as an independent event, then we can simply multiply the probability for each experiment to get the joint probability. Am I right? Okay, so this is how we calculate this. Am I right? Any questions? So yeah, this is very important. I would rather go slowly to make sure everyone.
Oh, okay. Now I see the value.
Go ahead.
The one minus p to the 50. That's the chance of it. That is the chance of it not happening.
Yes, that's the chance. That's the joint probability for you to see 50 tails, because in this experiment, this guy tossed a coin for 100 times, right?
Mm-hmm.
So if we want to calculate, so okay, let me show you this. So if you just toss the coin one time and end up with a head, so what's the probability to get that?
50.
What's the probability?
0.5.
No. So far, we need to figure out if this probability equals to 0.5 or not. So that's the parameter we want to estimate, right? So if this is a fair coin, yeah, P equals to 0.5, right? But if this coin is not a fair one, so let's say, so it's a uneven one, so the chance of getting a head is a little bit more, like 0.6, and probability of getting a tail is 0.4, add up to 1, right? So in this case, let's say this. So P equals to 0.6. So if you toss this coin and end up with a head, what is the probability for that event, single event? 0.6. 0.6, yeah, right? Okay, now if you toss this again, you end up with another head. What's the probability? By assuming these two tosses are totally independent. Another 0.6, right?
Yep.
Then what's the chance for you to end up with these two heads by toss this coin twice? You can multiply these two probabilities, right? Because they are independent. So the chance for you to get two straight heads by these two tosses is 0.6 multiplied by another 0.6, which is 0.36, right? Okay, let's see. Okay, if this is not the outcome you get, if you toss this two, just erase the memory. So if you do this again, two tosses, if you end up with two tails, what's the chance for that?
0.4 times 0.4.
Yes, 0.4 times 0.4, that's 0.16, right?
Mhm.
All right, okay, then let me know, what's the chance for you to get the first head and the second tail?
First head, second tail, 0.6.
You raised the memory, so suppose you didn't
6
do
times
anything.
0.4.
Huh?
0.6 times 0.4.
Yes.
0.4.
Yes. How about the first tail, second head?
0.24 again.
Yes. Okay. Now you can understand here. So now we extend this experiment from 2 tosses to 100 tosses. What's the chance? What's the joint probability for you to see?
That's the probability of getting that looks like the probability of getting heads 50 times.
Yeah, I think I'm missing a term here. So we have to time this thing. Sorry about this. Using this
100.
coefficient, because we don't know which 50s are successful, so we have to multiply these things. Sorry about this.
So C is 50 over 100.
Yeah, C 150 means because we only knew that among this 100 tosses you have 50 successes, right? But we don't know which 50s among this 100 you have the success. So there's another chance. So we have to multiply this coefficient here. Sorry about this. But anyhow, yeah, this is the way I want to show you. So how we can calculate the probability of independent events. Is that clear?
Yep.
Okay, any other questions?
So I have a question about
Yes.
the likelihood function.
Yeah.
So the likelihood function is different from the event function, right?
It's proportional to that. Yes, that's a good question. So likelihood function, actually, that's a very good question. So, because I didn't mention this now because I don't want to confuse students if they do not have a lot of experience dealing with the maximum likelihood function. All right, so there are two versions of probability. So the first is the joint probability, which is here. The joint probability means if you already have the information about the parameter, right? If the parameter is known, given the parameter, what is the chance for you to get these results? What's the probability? What's the joint probability you're gonna get this series outcomes? So that's the joint probability. That's not the likelihood function.
Yeah.
Likelihood function is the probability of theta. Is the probability. Likelihood function is the probability of the parameter given data reversed. So if we want to say the likelihood function is actually something like this, probability function of theta given data, x1, x2,
X2.
and
Excellent.
but based on the Bayesian theorem, so you can rearrange this likelihood function, and finally you're going to see the likelihood function is proportional to the joint density function. All right, because this is a little bit too far, so I don't want to. So we're going to talk about this later, but not now, because it's too complicated. I try to introduce this MLE concepts in an easy way. So here I try to show you how we calculate the joint probability, right? Is that clear? Okay. Okay, now, so go back to our experiment here. So how many parameters do we have? Can anyone tell me? So here. So first, I have two questions here for you. So first, what is the model for us, probability model for us to model this table? And based on that model, what is the parameter we try to estimate? So here, this is the outcome, right? And outcome, let me give you some hints. So how many categories? So if you want to look into the progeny from this, all the progeny from this test cross, how many categories you can classify your progeny?
4.
2, yes, parental or non-parental, so, right? Parental type or non-parental type. So this is the parental type, and this is the parental type, and this is the non-parental type, and this is the non-parental type. Am I right?
Mm-hmm.
Am I right?
Yeah.
Okay. All right. Then, is this very similar to the tossing a coin? So if you think about, like, we have 1,000 progeny. So if you think each progeny, the genotype of each progeny is the outcome from one single toss. Does that make sense? Okay, so we can we can simply translate this experiment into a simple version, into a version that you are more familiar with. Like, so suppose we do this experiment, we end up with 1,000 progeny. Big N equals to 1,000. Now we have 1,000 progeny. We can do the DNA sequencing to see what's the genotypes for these two loci for each of these 1,000 progeny. Am I right? And then we can use that data. We can classify each of these 1,000 progeny into 2 categories, parental type or non-parental type. So this is exactly the same with the tossing a coin. So we can use the binomial distribution, right? All right. Now in the binomial distribution, we only have one single parameter, which is the P, the probability of being a success. Is that right? So if we define the success to be a recombinance, then P equals to R. Actually, we have a single parameter here, which is R. And this R is equivalent to the P in the binomial distribution. Any problems with this example? Okay. Any questions? Okay, so now, so without any derivation, without any calculation, I'm gonna give you this solution. So later I will show you how we get this solution. So based on this data, we can simply estimate this parameter, which is R. So I hope I didn't confuse you. So what is R here? What is R here? So although I just gave you an example of the tossing coins, don't be distracted.
Fractions.
So come back to our problem. So R is the recombination frequency. R is the recombination frequency we try to estimate. But it happened to be the same. It happened to be similar to the P, which is the parameter for the binomial distribution. Do you agree? Okay, good. So now we use this data to estimate. So intuitively, this is correct, right? So if you have this many progeny, big N, 1,000, and out of this 1,000, you see this many recombinants. Because this sample size is too large, it's very large. So we can just use this ratio to estimate R. Does that make sense? Okay. Yeah, intuitively, this makes sense. But we need to find out the theoretical foundation for this. Why we can use this way to estimate R, because this is related to the MLE, maximum likelihood estimation. So I try to link the problem, our problem, to the theorem. So here I try to introduce the MLE to maximum likelihood estimation, because we want to use data to estimate the parameter. Now this is the data we have. Oops. This is the data we have. How can we use this data to estimate this parameter R? We can use MLE. Is that clear? Is it too tough? So do you need me to repeat this? Okay, good. Okay, so now let's go back to here. So this example is okay, right? This example is okay. So suppose we toss a coin, like, because we toss the coin. The purpose for us to do this experiment is to estimate P. What is the P here? The P is the probability of being successful, or the probability of landing a head, right? Right? So we want to estimate that P. So we don't know if that P equals to 0.5 or something else. So we can do this experiment, all right? And we toss this coin 100 times. And this is the data we can get, right? And once we get this data, so how can we estimate this P? We can simply use the ratio. For example, the ratio of what? The denominator should be 100, right? Because that's the total number of the trials. And the numerator should be number of the heads showing up, right? So this is intuitively, yeah, this is the way we can estimate this P, right? Does that make sense? Okay, now try to translate this experiment into our project. So this project actually the same. Suppose we toss the coin 1,000 times, which means we do this experiment, we end up with 1,000 progeny. And because we don't know, well, for each progeny, so we can define each progeny by checking the genotype for these two loci, right? And once you check that genotype, so can we comfortably put any of this progeny into one of two categories, parental type or non-parental type, right? So this is equivalent to put each progeny into heads or tail. Can we? Because two categories, right? Parental type and non-parental type. If you label the non-parental type as a heads, parental type as a tail, that's exactly what we were doing about the tossing coins, right? Okay, now here R is equivalent to the P, the probability of being a head. R is equivalent to that, right? We use the same model. So if this is true, so how do you use this number to estimate this R? It's easy, right? So we use the number of a progeny, which is capital N, in the denominator. Let me discuss this. Okay, look at here. This is what? This is the total number of tosses, right? And this is what? This is among these 1,000 tosses, how many trials end up with a tail? With a head. Is that correct? So these two models are actually identical. All right. So right now, I just give you example and the solution for this. So later on, I'm going to show you how we can use the MLE, the maximum likelihood estimation, to get this solution. Look at here. This is the solution. So why we can use this formula, the ratio, to estimate this. So this is why we can. Right? So today, I think, yeah, so I think it is a little bit slower than what I expected. So if you don't, if you agree, so I'm gonna use another 30 minutes to continue the lecture. Is that okay? Okay, thank you. So far, any questions? Any questions about this? Okay. All right. Now, since we can use the binomial distribution to model this experiment, any questions, any problems with this part? So this is important. I try to link the tossing coin to our own project, right? So here we tried, we just justified that we can use the binomial distribution to model our experiment. Okay, now here, this is the parameter we're gonna use. Given this parameter and these observations, this is the probability, join the probability, we're gonna observe this data, right? Any questions? Okay, now the likelihood function. So as I mentioned, the likelihood function is actually proportional to the joint probability. All right, so we can remove some irrelevant part and just leaving the principal part here. So that's the likelihood function. And so because likelihood function is not easy to deal with, we usually do the log likelihood function. We log this thing. So the exponential becomes the sum and the multiplication here. Does that make sense? Okay, good. All right, that's the log likelihood function. And how to use this log likelihood function to help us to find the solution, the best value for R, the parameter, that can maximize this likelihood function, log likelihood function, all right? Am I clear? Am I clear? Okay, so the target, so now we successfully constructed the maximum likelihood function, and how, the next step is how we can use this function to help us identify the best value, the optimal value for R, which can maximize this log likelihood function. So suppose this is the log likelihood function. So if we want to maximize this, so it's easy to do the first derivation and find the first derivation equals to 0, right? So the first derivation equals to 0 is the position where the maximum likelihood function will be maximized. The likelihood function will be maximized. Am I clear? Okay, from here, so this is the log likelihood function. We want to find the R, which is here. For example, here, we want to find the R which can maximize this log likelihood. So the log likelihood is the curve like this. So obviously there is a maximum value here. So how to identify this R that can maximize this log likelihood? So we just do the first derivation and set this to 0. This way we can identify this position and this R here. Is that clear? No? All right, okay. Then ignore this part for now. So I'm gonna come back to this later. So let's move on. All right, so when we do the first derivation, this can help us to identify the R, get the solution for R. This is the maximum likelihood estimation, MLE. And we also need to do more. So based on the first derivation, if we do the second derivation, we can get this quantity. And this, we name this as a H matrix, H value. And if we do the expectation of this, this gives you another term, information, Fisher's information. And this is important because Fisher information is a way for us to measure the amount of certainty about the parameter given the data. And if we look at here, so if we inverse this in Fisher's information, this gives us the variation of the estimation of the parameter. So at the first step, we already get the estimation for this R hat. But now we want to see how accurate we can estimate this parameter. We need this term, the variation of this estimation, and this gives us the standard error. And usually when we do the statistical analysis, we need to report two things. One is the estimation itself, and the other is the standard error for this estimation to show you how accurate your estimation would be. So this is what we do here. Any questions? Yeah, this is, I know this is very, very hard. It's solid. Let me give you some like interesting part to end today's lecture. All right. So here, go back to our problem. The first question is to test the linkage. So now, don't think about the tossing a coin. Don't think about like the function, maximum likelihood function, because it's difficult. Now go back to our problem. So we want to test the linkage between A and B, okay? Now, if you get a value of R, you want to see if this R is significantly different from 0.5 or not. Is that correct? Because we want to test if these two genes are linked or not. If they are not linked, the R should be equal to 0.5, right? Am I right? If the two loci are not linked, the R between these two loci should be equal to 0.5. Am I right? Okay, so this is what we want to do next. So we want to test the linkage between these two, A and B. Now, alternative, so this is equivalent to test this hypothesis. We want to test if the R, which is calculated from your data, is equal to 0.5 or not. There are two hypotheses here. One is that, so in a statistical test, there are usually two hypotheses, competing hypotheses we want to test. So the first one is the non-hypothesis. So this, we label this hypothesis as the H-non. Usually we put this hypothesis, non-hypothesis, on a trial. So if our data fit or support this hypothesis, we're gonna accept this hypothesis. Otherwise, if the data is not supportive of the non-hypothesis, we're gonna reject the non-hypothesis and take the alternative hypothesis. So in this case, if you already have your data from the test cross, and you can use that data to calculate the R, right? R estimation. Now, suppose, for example, if you your calculation shows that R hat, which is the estimation of the R, equals to 0.41. Does that mean these two genes are linked or not? I don't know. I need to make a test. So I want to test if this R, the realized value of R, which is the 0.41, is close to is close to 0.5, or it is far removed from 0.5 to show a strong linkage. So this is what we want to do, right? So we put the R hat equals to 0.41 on a trial to see if this data is supportive of the non-hypothesis or not. If the data shows, okay, yeah, this R is close to 0.5, the probability is big, then we're gonna accept the null hypothesis. Okay, these two genes are not linked. They are totally independent from each other, right? However, if your data is not supportive of your null hypothesis, we're gonna reject that one, and your conclusion will be, okay, the data is not it's not supporting the null hypothesis. We're gonna reject the null hypothesis, which means we're gonna take the alternative hypothesis here, and R is significantly less than 0.5, showing a strong linkage between A and B. Yeah,
sorry.
Go ahead.
What should be like the cutoff for the probability? Like, what probability do we consider as high so that we can say that these are not linked? Or
Good question. Yeah, so this slide shows that. So usually so for example, this is a non-distribution, because as I mentioned, in each statistical test, we only test the null hypothesis, right? We only put the null hypothesis on a trial. Suppose this is the non-distribution for the null hypothesis, and so don't think about this mu zero. Just think about this R equals to 0.05. This is the non-distribution, all right? Now, based on your data, you can calculate something like 0.41, 0.041. Oh, is that clear? So, okay, so the red curve shows the non-distribution. So suppose if there's no linkage at all, you're gonna see, so if you repeat this experiment, each experiment you're gonna end up with an estimation of your R, right? So for the first one, you're gonna end up with the 0.41 here. Maybe second one, you're gonna end up with a 0.3 here. So that's the distribution of your estimation, right? Is that right? So if your non-model is true, so all this repeated measurement should end up with a R estimation within a reasonable range. The difference between each experiment is because of the sampling error. Is that right? So if your estimation is close to this point, so that means like we will accept the null hypothesis. However, if you did an experiment and this experiment, based on that data, you end up with a very small value here. What does that mean? So if you did an experiment and that experiment gives you 1,000 progeny, right? And you classify this 1,000 progeny into two categories, parental and non-parental, and you use that ratio to calculate R hat, right? And if that R hat, based on your calculation, is equal to 0.1, what do you think? It is far removed from R equals to 0.5, which means your data is not supportive of your null hypothesis. So in this case, you're gonna reject your null hypothesis and claim, okay, there's a strong linkage between A and B, right? Then come back to your question. We need a criteria to show how far is far enough for us to reject the null hypothesis, right? So this is, usually this is, so suppose this is a normal distribution, but this is not related to our real problem. I just show you a normal distribution, okay? So usually based on a distribution, we will define a region, small region, and the area of these two regions add up to alpha. And the alpha is defined as the significance level. So based on the rule of thumb, so most of people accept alpha equals to 0.05. Yeah, which means if your null hypothesis is true, so it's possible for you to see the distribution covering this area. But if your data, realized data is within this region, which is very close to the center, right? So if you realize the value is within this region, we think, okay, you observe the deviation from the center is totally due to the sampling error, and it is still following the non-distribution. However, if your data goes way beyond here, so this is a strong evidence against your non-hypothesis. Because why? Because if the non-distribution is true, the chance for you to get a value to here is extremely low. Do you agree? Because if you extend this, the chance of getting this value is extremely low, right? Am I right? So here, so we always define a significance level, which is the shaded area here, and use this as a criteria to help us to do the statistical test. Am I clear? And yeah, your question, the answer to your question is like, usually we use 0.05 as a cutoff, as a p-value to show whether we should accept the non-hypothesis or we should reject that non-hypothesis and take the alternative hypothesis.
So if we get like an R of 0.4, which is close to like
yes.
10.
So
But the probability will be like 1%.
0.6 or something.
Yeah, something like that.
Yes.
We shouldn't accept that R, right?
Yes, we should accept the non-hypothesis, which means there's no linkage between A and B. But if you like end up with a R here equals 0.1, this will give you a probability something like 0.001, and that's a strong indication. No, I don't believe non-hypothesis is true because the data is against the non-hypothesis. The p-value is actually the probability of observing the results you get from your data given your non-model is true. So if the p-value is small, means like, oh, so if non-model is true, it is unlikely for me to get data like this. So that's very bad. So I'm gonna reject the non-hypothesis and take the alternative one. Does that make sense? Okay, very good. So this is this is my favorite part. Oops. So the logic behind the hypothesis testing. So this is very similar to what is happening in the court in this country. So basically, so for example, we have a non-hypothesis. This is a very nice country. So we usually assume any guy on a trial is innocent. So that's the non-hypothesis. Okay, an alternative hypothesis what is, okay, this guy is not innocent, right? It's guilty. But yeah, we want to test the non-hypothesis, which he's innocent. And we put this hypothesis on a trial. Based on this hypothesis, we collect data, we do experiment, just like we did, right? So once we have a non-hypothesis versus alternative hypothesis, so we want to put the non-hypothesis on a trial. Based on the non-hypothesis is true. Based on the non-model, we collect the data, and then we test if this data is supportive of the non-hypothesis. If the data support the non-hypothesis, which means the probability is big, there's a reasonably big probability, then we're gonna set this guy free because yeah, the data is supporting the non-hypothesis, which means he's innocent, right? Right? However, if the data is not supporting the non-hypothesis, what happened? Yeah, the p-value will drop, a significant jump, which means if non-hypothesis is true, which means if this guy is innocent, the chance of getting this data we collected is extremely low. So then we don't believe the non-hypothesis is true. We're gonna put him in jail. So this is exactly the logic behind the non-hypothesis we are doing. So remember, when we do the hypothesis testing, we always put what on a trial? my question is, so when we do a hypothesis testing, first, we have two hypotheses, right? We have non-hypothesis. We have an alternative hypothesis. They are conflicting with each other, right? Now, if we want to do a test, which hypothesis we're gonna put on a trial? We just test the non-hypothesis.
Non-hypothesis?
Yes, non-hypothesis. Very good. We only test the non-hypothesis, right? We have two hypotheses, non and alternative hypothesis, but in a test, we only put the non-hypothesis on a trial. So if the data is supporting the non-hypothesis, we're gonna accept it. Otherwise, we're gonna reject it and take the alternative hypothesis. So we don't put the alternative hypothesis on a trial. We only put the non-hypothesis on the trial. All right, so this is another example. So, okay, so let me show you. Okay, so suppose with a very short notice, you are invited to a very important party tonight after work. So you, of course, you want to become the focus of the party. So you need to pick a beautiful dress for yourself. So after work, you rush into the department store, but you really do not have enough time to try two dresses. So you're gonna make a choice between these two dresses. You put one labeled as your non-hypothesis, another one is the alternative hypothesis, two dresses. So you're gonna choose one of this, but you do not have time to try both. So what you do is like, you just put this one, which is labeled, oops. You put this one on yourself and look into the mirror. Yeah, you see whether this fits you or not. If it fits, and then you're gonna take this one, right? You're gonna take this one and go to the party and become the focus of the party. If when you look into the mirror, if it is not that fitting you, so you're gonna reject this one, and without trying this one on, so you just grab this one and go to the party, because so you think, yeah, this one will fit you better and make you the focus of the party. So this is my favorite example. I always throw out this to show the logic behind the hypothesis testing. Now, yourself is the data. Yourself is the data. Now you have two competing hypotheses. One is the H0 and the other one is the alternative hypothesis. You cannot try both of them, so you just put the non-hypothesis on yourself, fitting, to see. Yeah, you want to see if yourself data is fitting this non-hypothesis. If the p-value is great, which means p-value is what? P-value here is the probability to become the focus of the party if you put on the first dress, the non-hypothesis dress. Okay, so if this p-value is large, which means that you believe H0 is good, you're gonna take this one. Otherwise, if this p-value is small, which means what? Which means like if you put the H0 dress on, the chance for you to become the focus of the party is low. So you're gonna reject this one and take the alternative one. Is that clear? Do you like this example? All right, I think I'm gonna stop here. So any questions for today's lecture? All right, so before we leave, so I'm gonna briefly summarize what we have learned today. Okay, so at the very beginning of the class, so we finished talking about two kind of map functions, right? Haldane and Kosambi. All right, they are equally good. So they are equivalent to each other when we talk about the distance, small distance and a large distance, right? They are only different in between because they are based on different assumptions about the interference. Is that right? So this is what we have learned for the first chapter. And the second chapter, we just introduced introduced a special design. So why do we introduce that design? What is the design first? So what the design we introduced today? Backcross, yeah, backcross. So backcross. So next time we're going to talk about F2. F2 is more complicated because backcross design only gives you 4 categories, genotypes, and the 2 categories, phenotypes, parental type and the non-parental type, right? But if we are talking about F2, so that gives you more categories, so more complicated. So we start from the simple one, the backcross design. And when you have a backcross design, the purpose is to use the data. The data is what? Is the progeny from this design, right? So we can generate, for example, 1,000 progeny, and then we can use the genotyping strategy to examine each progeny to see what's the genotype for these 2 loci in each progeny, right? And then we can classify this 1,000 progeny into 2 categories. What are these 2 categories?
Parental and non-parental.
Yes, very good. Parental and the non-parental type. And this is very similar to the tossing coin experiment, right? So the purpose of doing this experiment, get the data, is to estimate something. What is the something we want to estimate?
Recombination frequency.
Yes, very good, R. So R is the thing we are interested in, but we don't know that thing. So that's why we want to use the data to estimate. That's why we use a little hat and put the little hat on R, because that's the estimation, right? Yeah, because we use the data to estimate that, but the estimation is not equivalent to the real R value, because when you do the experiment, you get a sample. The sample, even the sample is big, but still is small compared to the entire population, right? So you can never estimate the parameter 100% accurately. So there's an error. There must be something called the error. So that's why we want to use the data, not only to calculate the R hat, which is the estimation for the parameter, but also calculate the standard error for this estimation. Gives you some way to do the test. All right. So we didn't go deeper to talk about the MLE. So maybe next time. So on Thursday we're going to talk about that. But we did cover the logic behind the hypothesis testing. I hope, yeah, those 2 examples gives you a strong impression. So hopefully, so usually my student when learn about these 2 examples in the future, for the lifetime, they understand what is going on in hypothesis testing. So in hypothesis testing, so hypothesis test is for addressing a specific scientific question. For example, here we want to see the scientific question we want to address is whether these 2 loci are linked or not, right? So any test is for answering a specific scientific question. Okay, now to answer this question, you have 2 possible solutions, right? Either yes or no. So yes or no, these 2 loci are linked, or they are not linked. So you have 2 ways to answer this question. That means you have 2 hypotheses. So non-hypothesis, which is the no linkage, and the alternative hypothesis is the linkage between A and B, right? Okay, because we do not have time to put both stresses on, so we just put one. We just put the non-hypothesis on a trial to see if our data fits this hypothesis or not. So how do we know our data fits this hypothesis or not? So we calculate the p-value, or based on the assumed probability model to calculate the p-value, right, for this test. If the p-value is bigger than 0.05, let's say, which means, okay, there's a quite strong evidence showing that the data is supporting your non-hypothesis. So in this case, we're going to accept the non-hypothesis. Otherwise, if the p-value is extremely low, which means given your non-hypothesis, given your non-model, the chance of seeing data like this is tiny, which means it's impossible for you to get this data if you believe the non-hypothesis is true. So in this case, we're going to reject the non-hypothesis and take the alternative one. All right, any questions? All right, so if you do not have questions today, so we're gonna stop here and see you next time on Thursday. And okay, thank you everyone. Bye-bye.